Okay, so now we are at page 102. So we are calculating the probability of false alarm and then probability of detection. So probability of false alarm is equal to probability of threshold larger than no, the test statistic larger than the threshold condition on H0. Because when this happens, you are making a decision for H1. And then under H0, you decide H1, that is a false alarm. So you have Q function, right? You have a Q function because of what? Because of uh, because of this uh, because of this distribution. You just divide it by this, then you get uh, Gaussian distribution with variance 1. So what happens is uh, for this to be larger than 1, you divide this t by this square root of epsilon over sigma square. Then the right hand side, which is the gamma prime, is also divided by this square root of this thing, and then it's like you have a Gaussian distribution. You have a Gaussian distribution, and you are calculating the tail probability, right? You are calculating the tail probability, the tail. So as a result, what happens is it's a Q function of this thing. If it's a standard Gaussian, then it's a Q function. And then PD again is T larger than this gamma prime condition on H1. However, for T to be conditioned on H1, it actually has a mean for epsilon. It has a mean for epsilon. So you have sort of have to minus epsilon, and then of course gamma prime will minus epsilon, and then divide it by square root of this, and then of course the right hand side divided by this, then it becomes a standard Gaussian. And then when standard Gaussian is larger than something, it goes back to this standard Gaussian Q function tail probability again. So you will get this Q function of this, Q function of this. Okay. So, so um, uh, Q function, this is just reiteration because I think in previous chapters we have been discussing this couple times. So it's a standard Gaussian. This is a standard Gaussian distribution, and you go from x to infinity, which is the tail probability. And of course, it could be 1 minus this phi, capital Phi of x. Capital Phi means the left-hand side. It's the left-hand side of the standard Gaussian. And it's also, of course, this also called a cumulative distribution function for a standard Gaussian. So it's a sort of the CDF for a n01 random variable. Now, since the CDF is a monotonically increasing function, Q function is a monotonic decreasing. So, as an inverse function Q inverse, this is minus one is not exponent. It means the inverse function. Okay, inverse function. So as a result, gamma prime has to be equal to this PFA. How come we are able to get this? If you see here, you see something here. You take the inverse function of PFA. Notice that uh, we are trying to set a threshold on PFA. That's Neyman Pearson, right? So uh, Q inverse function of PFA will give you gamma prime over this, and then you multiply it back. You get you get this you get something like this. So this is also trivial. And then, of course, then you can substitute into what? Into PD. Remember, PD is a function of gamma prime. And now we are getting gamma prime as a function of PFA. As a result, we will be able to construct the relationship between PD and PFA. That's the point. And the intermediate variable is going to be gamma prime. So we will substitute this gamma prime in PD as a function of gamma prime, and then do some simplifications. Then you get PD as a function of PFA. And of course, there are some outside variables such as epsilon, sigma square, and Q function, and those things are all known. Okay. So uh, again, we are setting a new variable that's called eta. Eta. That eta is epsilon. We will just give it a new name. Give this whole thing a new name. That's called eta. That uh, maybe I should pronounce eta. That eta uh, equal to epsilon over sigma square. That is the kind of uh, if in some cases we will call it SNR, signal to noise ratio, but uh, mathematically you know what it is just epsilon over sigma square, but in many cases we'll interpret it as signal to noise ratio. Okay, so PD, if this increases, then that decreases, so PD increases. So uh, it's kind of we can we can build relationship between PD and PFA. However, it's dependent on this on this constant, and this constant is we call it eta, and it's called energy to noise ratio or signal to noise ratio. It has many different names, or SNR, signal to noise ratio. It has different names, but uh, it doesn't matter as long as you know what it is in your context. It doesn't matter. Okay, so now we have this SNR as the parameter. Okay, so now we have PD as a function of PFA, and then of course if we fix PFA, then we can think of PD as a function of eta, right? Eta. So the other example is the DC level example that we mentioned in our previous sessions. Then the energy part will be Na squared. So eta will be Na squared sigma squared. It is apparent from the curve that to improve the detection performance, we can always increase PFA or increase the ENR, or you like to say SNR, it doesn't matter. So increase the signal energy, either by increasing the signal level or signal duration. That is consistent and understandable, right? Think about it. In the DC level problem, if your DC level is very high, then you can expect the performance to be better, right? Or the other thing is if you increase the time, which is the signal duration, right? This is sort of like if the signal is not that good, you want to collect with a longer duration. You like to collect over a longer time period, then it gives you better performance. So either way, it improves your performance. So the shape of the signal does not affect the detection performance, right? We have talked about epsilon, which is the signal energy, but here the signal S is summarized sort of in this signal energy. So the shape becomes insignificant here, right? So in this figure, let's take a careful look. The detection performance and the horizontal is ENR, that is this, except it's in log scale. We take the log 10 multiplied by 10, which is the dB scale, the dB scale. And then the probability density function. Of course, based on this equation, we know that we have to give it a PFA, right? So a PFA equal to 10 to the minus 1. Then we have curve like this. With the increased SNR, we have better PD. And then with this 10 to the minus 2, then we have curve like this. Of course, if we are asking for a lower PFA, we are going to suffer in PD, right? As I mentioned, the best thing is you want to reach a point where it has very high PD and very low PFA. But here, uh, if you have low PFA, then you see the PD goes from here to here. As a result, you need to sort of increase the SNR to make the PD better. That's the one aspect to look at this equation, 4.14. Okay, and now let's uh, go to the next page, 104. This is to mention that a signal with different shapes. For example, this is 0, 0, 0, A, 0 to A, and this is A, 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 A. If you take the signal energy, you have A squared, phi A squared, right? And you take the signal energy for this one, you still have phi A squared, which yield the same detection performance. Okay, so sort of this I think this is a very good uh, outcome, which gives you a PD and PFA, and then you can illustrate it. Okay, so we'll skip some of it. Then we go to this generalized version of the match filter. Generalized version means that um, when we have a noise, the noise is correlated noise. It's no longer white noise. As a result, you have a covariance matrix, and that covariance matrix gives you covariance of the noise for different time between different time differences. So for example, this CRV of Wm and Wn, in our previous case, it is supposed to be 0 if m is not equal to n, but here is no longer 0. So the C will be a covariance matrix. The C will be a covariance matrix. So this is, of course, obviously more generalized version, right? This is a more generalized version. So now we'll be calculating the likelihood ratio under such assumptions, which means non-zero covariance among different time difference. Okay, so now we try to write down the p of x condition on h1, and that is the multivariate. Recall, recall multivariate Gaussian. That's a multivariate Gaussian PDF. And then, as you can imagine, uh, it has this s as the mean. So there is a x minus s here. But if under h0, then there will be zero mean, right? Zero mean. Under h0, it's zero mean. So its multivariate Gaussian will be something like this. Will be something like this. And then likelihood ratio will be uh, L of x, this over this, this over this. But we are taking log. We are taking log. And then there's a log gamma. So it's a matrix version of the derivation. So if we just take a look at this L of x, then go through the derivation, at the end, we are getting this. It's a function of your sample and signal. And then we will incorporate the non-data dependent term into the threshold. How come we like to do that? As we said, if this is something we know a priori, it doesn't bother. We don't have to bother ourselves by putting this term here. We can just put it into the threshold, because threshold is the thing we are trying to decide, right? But since we are deciding a a sort of a constant, undecided, we don't have to bother ourselves to put an extra non-constant here. We just put it at the right hand side and then name it a new name. Name it a new name. This is sort of like a change of variable as we did before. So now we can, originally it's supposed to be this larger than some kind of threshold. Now we just discard this term into the right hand side, and then you you are left with this data dependent part, which is this larger than gamma prime. Okay, so but notice that for white Gaussian noise, which means that C equal to sigma square I, the detector will reduce this back to our original thing. This is the original match filter, right? But this is only true if C is equal to sigma square I, but in the generalized version, this is untrue. So uh, it's just a double check for our previous outcome. And now this detector, which is this one, is referred to as a generalized correlator or match filter. This is generalized because of what? Because uh, it has a sort of a, a generalized version of the covariance matrix C minus 1. So we can, of course, the C is supposed to be known. Then if this is known, we can do again change of the variable C minus 1s, make it a new notation S prime. As a result, this xt, which is from here, right? We can just give it a new name S prime, then it becomes xt transpose S prime. So that it becomes simple. It becomes simple. Except that the signal has to be sort of processed by this C minus 1. Okay, so let's take a quick look at some just a couple example. For example, this example 4.3, uncorrelated noise with unequal variance. So if this Wn is distributed this one and the Wn uncorrelated, which means that its C is diagonal with this And of course then the C minus one will be simple. It will be just, you know, it will be just the to put this sigma at the denominator. And then this is obviously unequal variance, right? Unequal variance for what? For noise, W. So we will decide H1 if this, then this will be a detector. It comes from here, right? We will just do this, put this into here, and then we get something like that. Okay, so this is unequal variance. Unequal variance. Okay, so I think that's good enough for this session, and we'll take a break and come back soon.